I will try to suit it without much pausing and I won't do much editing, okay? So let's give it a go. So you can describe a quantum mechanical system by a wave function which is a vector. Now the vector can be expanded by in terms of the basis vectors. So let psi be our wave function and 1, 2, 3, etc. are basis vectors, and a1, a2, etc., a3, etc. are the coefficients of the basis vectors, which can be complex numbers. So there can be infinitely as many basis vectors, but for our simplicity, we will consider the case where we have only two basis vectors. So the overall wave function is psi is equal to a1 1 plus a2 2. So it is the superposition of 1 and 2. Now we use two vectors to describe two different outcomes. Say we have a case where there is a particle and its spin can be +1 or -1. So there are two outcomes. So we use two vectors. So how can you get the probability in case of quantum system? You need to take the modular square of the coefficients of the basis vectors. So probability of measuring 1 is a1 star and 2 is a2 star. This is the Bond's rule. This is Bond's rule. Now also for simplicity, let's say a1 is square root half, then the mod square a1 star is half, that is 50%. So the other one will also be 50%, a2 star. It is also 50%. And why is it so? Because the probabilities must add up to 100%. It can be described in another way. We can say probability for a quantum system is equal to the summation of I, and it is a I, the mod square of ai. Now I can go from 1 to n, and here I is 2, so we have two terms. Suppose you have a quantum mechanical system which is in superposition of +1 and -1, two spins. You will never measure the superposition itself, but you will measure only the classical probability, either +1 or -1. So we are using superpositions with equal probability, that is half and half. So we will have both a1 and a2 equal to square root of half. So our overall wave function becomes psi is equal to square root of half 1 plus square root of half 2. But in quantum mechanics, the coefficients may as well be complex numbers. And if we are to consider one of the coefficients a complex number, we just multiply it by e to the power or e raised to I theta, where theta is a real number. And how is it so? Why are we introducing a complex entity? Think about it. Introducing a complex number doesn't change anything about the system or about the probabilities, because when we are to get the probabilities, say for the case 2, what we will do, we will take a2 star. In case of complex number, that will be this thing squared and e to the power minus I theta. So what will happen, both these two terms will cancel each other out, and we will end up with half the same probability in without considering the complex case. So the introduction of complex number is absolutely fine. You can do that too for this one, but we don't do that for our simplicity. And here the theta doesn't matter at all. Oh, and keep in mind, if A2 is a complex number, A2 star is the complex conjugate. Here theta is called the phase of the wave function. And why is it so? Because you can decompose the complex number into a sine and a cosine wave. So if you plot this thing, it will in 3D it will look something like that. So the theta is called the phase, and this thing is called Euler's formula. You may have learned it in maths classes. Now keep in mind, theta usually appears for oscillations, which I have shown earlier, this thing oscillation. But here is no oscillation because it is time independent. So there is no time dependence. Rather, it is a matter wave, not a time dependent wave. Now since we never measure superposition, we take decoherence, the idea of decoherence, into account. Now, what is decoherence? So, it is the phenomena by which a quantum system loses its quantumness, i.e. superposition and coherence. Now, let us consider an initial time and then let the particles travel to the detector from the source. It is the source and it is the detector. It is D, okay, not O. So now when a particle travels to the detector, it is bound to interact with many other particles on its way. So let's say it is our particle, and it will interact with many other particles like air molecules, etc., on its way up to the detector. And upon each bump, the phase psi, remember the phase, this term phase, the angle, it will change by a tiny bit. It will change by a tiny bit. So for a large scale, we need to calculate the energy density matrix. And now the energy density matrix for a wave function is calculated by the Kate-Bra product of the wave function with itself. This denotes the Kate-Bra product. So if you do the multiplication, the steps are shown here. You will end up with a vector. Sorry, you will end up with a matrix which looks like this. These terms are called the diagonal terms, and these ones are called off-diagonal terms. So in our simple case, the energy density vector will look like this. If you remember or if you recall, we took A1 to be half and A2 to be 1/2 e raised to I theta. So we will get that if we put the values. Look at it carefully. These two terms, the diagonal terms are truly constant. They never change. 1/2 never changes, okay? But these two terms, 1/2 e raised to I theta and 1/2 e raised to negative I theta, they will change. Why? Because theta changes with every little bump, every single bump. So in this case, we will need to take average of every value of theta. So let's say we have theta like this, like this. We'll need to take an average, okay? In this case. And how will we do that, and what will we end up with? Let's check for once. So you remember the complex number system? This is the real axis and it is the complex imaginary axis. Now for the absolute value, which is 1, let's say we have e to the power I theta. So the Euler's formula is, if we expand it, it will become cosine theta plus I sine theta. Now, so let's see, wait a minute, it will be 1 negative 1 I negative I. For a complex number, let's say we have 1, okay? Then square root of -1 is I, as we know. What will happen if we, so we have I here. We are here in this position, okay? Now we multiply it with another I. The result is -1. So we end up with 90-degree rotation. We multiply it in, we multiply -1 with another I, we end up at negative I, another 90-degree rotation, again with another I. So negative I dot I is 1, and lastly another 90-degree rotation which we multiply it by I. So if we take the average, we will just end up with a circle. We end up with points on a circle. Wait a minute. Like this. So it is the average in this case. So therefore you will find the numbers of the form e to the power I theta, which is cosine theta plus I sine theta, for 0 less than or equal for theta, sorry, for the with the 0 less than or equal to theta, wait a minute, or which is less than or equal to 2 pi, it will form you a circle for the when you go from 0 to 2 pi. But did we really take average? No. These dots are really the random peaks, the random bumps, the random changes of theta. These ones are. But what is the average of the system? The average is 0. The average is actually 0, not this circle. It is not the average. The average is 0. It is the magic of decoherence. You will not get a point in case of average, but you will go to the center, which is 0. So what does it implicate? So the average of theta the average of this term goes to 0. So he will end up with this vector. In case of decoherence, the energy density vector will look like this. We still have the diagonal terms, but the off diagonals become nil. So why is it called decoherence? Because in case of decoherence, the random changes of theta destroys the ability of the system to interfere with itself, so no interference pattern will be produced. If you recall correctly, in case of a quantum mechanical system, it has a well-defined phase and it can interfere with itself. So basically what I'm trying to communicate is you won't get such a pattern like this, but which is true for quantum mechanics, but you will end up with this thing, a classical double slit pattern, CM, which is classical mechanics. You will end up with this pattern. In case of a double slit experiment, that's what I'm trying to communicate with you. So for this energy density matrix, we need to consider a wave function. Now, which wave function will give you this energy density matrix? The answer is nothing. No wave function exists that will give you this pattern. So let us again consider the original energy density matrix in case of 2D for the arbitrary wave function. So if we compare equation 1 with equation 2, we will have A1 star is half, which is true, and A2 star, which is also half and true, obviously. But we will, by comparison, we will end up with A1 A2 star is 0 and vice versa. That is A2 A1 star is 0. What is the problem with that? You will have either A1 equal to 0, A1 equals 0, or A2 star equals 0, or vice versa, that is A2 equals 0 and A1 star equals 0. And it is the decohered energy density matrix, because we had already told you A1 is a half and A2 is 1/2 I theta. So we end up with a contradiction. So we are no longer talking about a genuine wave function. So the energy density matrix after decoherence describes classical probabilities. The classical probability, what were the classical probabilities? For say you have the double slit experiment, what were the classical probabilities? It was either this one 1/2 or that one 1/2, right? And you ended up with that 1/2 and 1/2, right? Now remember, we started with two particles having spins +1 and -1, two quantum particles. But let's suppose we are talking about the universe. Now, universe is much larger than a tiny speck than a quantum particle, right? So it will lose its ability to produce interference pattern with itself really quickly by the fact that it is extremely large and heavy, right? If you remember the de Broglie wavelength, it was equal to h, which is Planck's constant, divided by mv. M is the mass of the object and v is the velocity. Now, in case of an entity like an electron, etc., the wavelength is observable and measurable. But for a macro object like, say, football or, well, the universe, it is not observable or measurable. So for universe as a whole, as a system, you are not gonna have superposition. You are not gonna have superposition, and you won't get another universe by the virtue of splitting Y, because there is no superposition to begin with. You are not. So you say you are tossing a coin, right? You are either gonna get head or tail, right? Not a head and tail in a superposition. No. You are either gonna have head, the probability of which for an unbiased coin is half, and tail, which is also half. But when you do it is before measuring, right? Half and half. But when you have done the measurement, you either have head, then the probability is 1 because you saw the head, right? So it is 1, and tail, which is also 1 after the measurement. So the concept of multiverse is just fantasy. It is good for movies like Avengers, etc., and even the Amazon Prime series Invincible, but not in real life. It is really enjoyable. I can attest to the fact, but it doesn't work in quantum mechanics if you know some quantum mechanics. And decoherence is a basic part of quantum mechanics, and not only of the famous Copenhagen interpretation, right? Because without it, you will always end up with a quantum system, but we don't observe quantum systems around us. You can clearly see a tree, right? And the experiments like Schrodinger's cat, etc., are also false, because it is just a thought experiment, not a real thing. Why so? Because in case of Schrodinger's cat, you have a cat. Excuse my drawing, I can make better drawings, and check my Instagram for that. In a box, a cat in a box, right? And you have some sort of poisonous gas or something like that. In case there is a decay, right? The whole thing is put in another system which is enclosed, and in case of decay, he will end up with the exploding vial of the gas, and you will get the cat either alive or dead. But the cat is not a quantum object. It is not a quantum object. So the wave function of the cat is not like alive and square root 1 over 2 dead. No, sorry, excuse me. It is not like that, but rather it is either alive or dead. So you are dealing with classical probabilities. Alive is one half, death is one half. But when you observe the cat, you are either going to see it being alive or dead. So, and why is it so? Because cat's classical object, not a quantum one. So it is interacting with air particles around it and so on. So the theta, remember theta, right? It decays really quickly, and the off diagonal terms converge to 0. So we end up with a classical system. And in that case, when you see a cat, you either see it alive, the probability of alive then becomes 1, and dead, or dead, which also becomes 1. So I think I killed 2 birds with 1 stone, right? Thank you for watching. Stay tuned. I might make more videos on such topics. And please be sure to like, share, and subscribe. Thank you. Ciao.